We are going to talk today about precast concrete walls for seismic resistance. Sri and I have been working together for longer than we both want to remember, back since PRESS started a long time ago, into current research that he's going to talk some more about towards the end of this seminar. All of this research has been sponsored by NEES, and the seminar is by EERI, National Science Foundation, and NEHRP are other sponsors. So to get right into the program, this is our basic research team for the NEES Rocking Wall Project, which is also called the PreWEC project. Sri Sridharan is the PI, along with Kathy French out of the University of Minnesota. Eric Musselman out of the University of Minnesota Duluth is doing the testing on the anchorages, which Sri will talk about later. And I am the token practicing engineer. So any of you practicing engineers out there, if you have comments, send them to me and I'll make sure they get into the research, or at least I'll do my best. Today we're going to talk about the background of how we got to where we are now, and then I'm going to pass the ball over to Sri, and he's going to talk about the future a little bit. To me, it's really interesting that we can go through some of this research and actually implement it into practice. It takes a long time to get there, but I'll sort of walk you through how we've done it on a similar project, and then how it can happen today for you practicing engineers right now. In 1998, we built and tested a 5-story, 2/3 scale, 60% scale building at the University of San Diego. It's shown here on the slide. It's a 5-story precast concrete building, like I said, 60% scale. There were 4 different frame systems in the north-south direction, which are in and out of the page from what you see here, and then the one wall system in the east-west direction. The wall was tested not just to the design earthquake, but actually 150% of the design basis earthquake. This was back when zones were used. The testing and research team, the testing was done, like I said, at UCSD. Nigel Priestley was PI. Sri was the guy in charge. I'm not sure what his title was at the time. And Jim Conley and Stefano Pompanen were also heavily involved in the research as grad students. I worked with John Stanton at the University of Washington to do the design of the PRESS building, and Lehigh University had a component that was analysis to validate both before and after the test. Our sponsors for that project, which was a major project and sort of kicked a lot of this off, were the National Science Foundation, PCI, and what is now called PCI West. It used to be called PCMAC. Out of that research project came a technology that is actually widely used today. It's the hybrid frame, precast concrete beams, columns. You can see the different components of the system here without the concrete there. This is the column. There's post-tensioning that runs the whole length of the frame, reinforcing steel that runs top and bottom that then provides the energy dissipation. There's a grout, fiber reinforced grout each end of this frame. And this system was shown to work really well and has been through the codification process and implemented. And I'm going to talk a little bit about how that happens. With the PRESS building and the hybrid frame, we actually started that project. That was started at NIST, which is now was National Bureau of Standards at the time. They did a research project to look into different kinds of precast systems. From that, and the sponsor, which was Charles Canco Builders, they obtained an ICBO evaluation report so that practicing engineers could actually implement the system. Along with that, the PRESS building was built and tested. That was one of the 4 frame systems, which resulted in a document called ITG 1.203, which is effectively codification procedures that one can use to design that frame. There was also some validation that Sri and some of his grad students did that was a PRESS validation report. Because at the time, we had some of these early buildings from 1995 down to 2009, there really wasn't a codified procedure that one could follow. And it's kind of risky for engineers to design something that's outside of the code. But it was done. The Pearl Street Garage we did in Oregon in 1995. This was actually before the PRESS building, but was based on the NIST reports. There was a project right near the San Andreas Fault done by KPFS that was the Stanford Parking Garage. Engelkirk did the Westside Media Center, which is in LA. KPFS did another one that was in the San Francisco Bay Area as well, a 9-story building. which was a combination with shear walls and frames. And then the pinnacle was the third mission apartments, also done by Engelkirk. It's a 39-story building in downtown San Francisco. And all of these buildings were designed and implemented prior to the codification of this hybrid frame system. But fortunately now, there's codified procedures that lead you from the IBC, which as engineers we need to design to ACI 318, which refers to another procedure, design acceptance document, ACI 374.1, which leads you to this ITG 1.2 document, which really gives you the steps by which you design this frame. Now, the reason to talk about the frame is because out of PRESS, there was not just the frames, but there was also a wall system. And this wall system has gone through the same process, but fortunately, we're further on in the codification process with this. So I'm going to talk about a little bit how one would implement this and not have to go through what as engineers of records we consider to be somewhat risky implementation of a system that is not in the code. The PT shear wall, precast shear wall concept basically has precast wall panels that rock on their foundation. The nice thing is it gives you reliable performance with little damage. I know a lot of times we think of damage in earthquakes as being concrete crushing, but very often that concrete crushing is actually caused by tension yielding first, which cracks the concrete, and then the crushing falls it off. That behavior just doesn't happen with these jointed systems. And so we get reliable performance with very little damage. We also have intentionally sufficient damping for high seismic zones, and that's calculated. It's not just random. And it's based on a rational design methodology, which is part of the entire acceptance criteria process for getting these systems approved. None of these things actually happen with traditional systems. They're more evolutionary in that we find things that work well. They get evolved through the code process, through research. This is much more intentional, if you will say. The way the rocking wall in PRESS worked is it was built with two wall panels, one on each side. These UFP, we call them U flexural plate connectors, are basically connectors that will roll and yield and provide energy dissipation without any kind of permanent damage other than the yielding of the plate. There's vertical unbonded post-tensioning in each of the wall panels and fiber reinforced grout on the bottom. The system then just rocks back and forth on the foundation, comes back to the end, and there you are. The wall panels are very simple to connect. This is the wall panel that was used in the PRESS building. We actually had armor angles at the ends of the walls to minimize the cracking that would happen in the end of the wall. This is the base wall panel. This was a pocket. We used post-tensioning rods in this panel instead of strands, but either one works fine. And with those, this was the coupler where the 4 rods came down. This is the upper panel. You can see the only connection between the two panels is the end rebar and the holes in the center, which is where the PT runs through. That makes it very simple for a precaster to build. The erection process is simple. The jointed connection between the two is designed to be stronger than the yielding, rocking yielding, and the shear sliding associated with that in the event of a big earthquake, so that it's all truly capacity protected. In the PRESS test, the rocking wall did exactly what we predicted. And this was where the Lehigh group came in and the UCSC group as well. They predicted that under the design earthquake, EQ3, we would get, or we designed it to go to a 2% drift. And as you can see, we came fairly close. But in addition, we had this larger earthquake where we actually pushed it through a 50% greater ground motion. The results of the test were very much what we would expect, or we did expect. You can see the blue line is, I think, is what we were predicting, and red is what we got, or the other way around. I'm not sure. They're very similar. And the base moment history, so as you can see, we actually do have energy dissipation, even though this system is very, very clean. And if you had a cast-in-place wall, you would expect that amount of energy dissipation to actually give you some substantial damage. You all know what the plastic hinge looks like, and it's pretty packed up usually. Well, at the end of the PRESS test, this is at the very end of the earthquake 3, so the design basis earthquake of 2%. That's what the end of the wall looked like. And at the very end of the 150% design basis earthquake, this is what we got. Just this little tiny bit of falling. A very, very clean performing system. In fact, when I went to implement it in one of my projects, one of the questions was, well, how can we tell if it's damaged? And the answer is it's not. The validation of these tests, it looks good, but is it real? And so Slytherin and Thomas and Slytherin went through an extensive evaluation of the design guidelines that we had prepared prior to the test and validated and made some minor changes to that. All of that testing was then followed. That was the PRESS 5-story building test. There was additional testing done on a similar wall system in New Zealand that had rebar to the base, which I'll show you in a minute. And then there's also a rocking wall modeled in a shake table test that was done down in San Diego in 2008. There were many, many other tests. If I start naming them, I'll get them wrong. These were just the three that I know in detail. But a lot of other professors, a lot of other research teams involved in this around the world. The nice thing as a design engineer is there are documents that I can follow. If I follow ACI ITG 5.2, it's really the same thing as following the code. It gives you the step-by-step procedures one has to go through. I will admit it's a little bit harder than just following the code, but it helps you with what you need to do. And the nice thing for a building official is it gives the building official something to check against. So they don't have to worry about those vague words called, equivalent strength and toughness. Those are hard to quantify. But with the ITG 5.2 document, if you want to implement one of these walls, you just follow this document that you can purchase from ACI, and you're on your way. The system, as far as I know, and again, this is just my limited experience, has been implemented back in, I believe it was 2002. The first one I know of was actually in the Dominican Republic. John Stanton, who was a major part of the PRESS research, helped with that implementation. There was a very innovative precaster in the Dominican Republic that wanted to implement both the frame and the wall, and he did so. There were also hybrid frame and precast wall systems built both in Chile and Christchurch prior to the earthquake. And the interesting thing there is, in both cases, they went through the rocking motion caused by these fairly major earthquakes and did exactly what they expected. And we are now involved in a project in California that's in design. I don't know if there's other ones that have been designed in California or not, but there may be. If somebody could send me a note on that, I would really appreciate it. This is the Christchurch building. I unfortunately don't have photos of either the Dominican Republic building or the building in Chile, but I know they exist. There was a report on the Chile building written by Ned Cleland and Neil Hawkins. It's in a PCI journal, I believe, that will talk a little bit about that system. But it went through the earthquake really well. This is the Christchurch building. It's actually a medical building, and that has a report on it as well. And this is a picture of the shear wall in the parking garage. This is the press wall with the UFP plates right there. This is a 3-panel wall, and it looks like there's not a scratch on it. And this would be before the earthquake, you'd think, but actually this is after the earthquake. So it's a pretty good system in terms of its performance. In San Francisco, the Bay Area, it's not in San Francisco, it's in the Bay Area down the peninsula, we're building a dorm complex, and in this system there's a precast walls pretty much at every unit here and between the units. We're designing the rocking wall here, not using the UFP plates, but using the type of system that was actually tested in New Zealand, where we have reinforcing steel at the ends of the wall and vertical post tensioning up the middle. But either one of these types of systems is allowed by this ITG 5.2 design guidelines. This is the one that we're using in the San Francisco project. This is the one that was done in the Christchurch building, although that had 3 panels, not 2. But it's fairly straightforward, both of them, to implement, and you just have to work through the steps. Now, when you actually go implement a building, it's very different than research, because unfortunately in our buildings, well, not unfortunately, but fortunately in our buildings, they're 3-dimensional, not 2-dimensional. And even though the press building was 3-dimensional, the shaking of it was 2-dimensional, one direction at a time. One of the things that came up when we did the press building was the concern about wall uplift. And this is also something that people get concerned about with the frames, with frame bay elongation. The same behavior. With the wall uplift, though, it's kind of interesting. We see it with a precast wall because of the jointed nature of the rocking behavior. But in reality, that same wall uplift behavior occurs in a cast-in-place wall. This is a comparison, and Sri's going to talk about this more in a little bit, where this is a PreWEC wall that was tested, and in the red, in terms of elongation or uplift at the left side here versus top drift, and it's very linear. We had another test that was done, I believe this one was in Minnesota, where it was a rectangular cast-in-place wall, very traditionally detailed, and it had uplift as well. In fact, it had more uplift for the same drift. And Sri's going to go through what that is and the whole correction thing. But this is a corrected version. You can see these two lines are fairly much the same. So while we see these behaviors in the precast system, they actually occur in cast-in-place as well. The other effect that we saw in the PRESS building that deserved more study, there's probably more than that, but was the outrigger effect. When you have a rocking wall, the concern was, when we did this building in PRESS, was how do we keep the dead load from the floor system from affecting the behavior of the rocking wall? And we had, on this building, we had double T's that span all the way from side to side on the first 3 levels, so that was pretty easy to just create a shear connection and not worry about any vertical resistance, because the vertical resistance just wasn't there. We were able to create a vertical slotted connection. But at the top 2 levels, we actually had a double T system that would span into the wall, so in and out of the page. And because of our concern about this outrigger effect, John Stanton invented this pin connection. Basically, it's a connection that would take shear in the wall, but not take any vertical load. And there was a channel that went the whole side. This is great. It works really, really well for the test, but it's not very practical to implement in the field. So the PreWEC system is being looked at to address some of those systems. And this is now Sri's turn. And I will now pass the ball on to him. If I can figure out how to do that.
I got it. I passed it on over. He should be ready to go.
Great.
So have you passed the ball, Jared?
Yeah, you have the ball. You should be able to share your desktop now.
Okay. I see there's one question and answer. I think Steve Huntsberger says he can't hear.
Yeah, I sent him a message. He should be able to connect by the phone conference.
Okay. All right. Okay, so I'm going to get into the second part of the presentation, which is going to touch more so on the current research that we are doing. I'll give a minute for the PowerPoint to upload and transfer to your side. So here's this outline that Susie presented. So I also appreciate all of you participating in the webinar, and of course the support from NSF under the leadership of Dr. Joy Powski, NEES COM for organizing this webinar along with EERI, and we have gotten support from several industry collaborators as well. And some of the findings that Susie reported is based on some of the completed research which was funded by PCI, PCMAC, and we also had other National Science Foundation project, along with the concept test that I'm going to be showing was actually partly funded by National Science Foundation as well as the National Science Council of Taiwan. So with that, let me just go back to the jointed wall system, what we tested, and point out one thing that we haven't achieved in this country, but several people have implemented outside the U.S. And the reason they implemented was because they were looking for better performing structures. And the reason we haven't implemented, perhaps, I would argue that the cost of the system is not as equal as the reinforced concrete or some other equivalent system, and therefore the jointed wall system has not been found to be a viable option for industry. So here are the shortcomings that one can identify. When you take a wall panel as shown here, and if you split the wall in the middle, what happens is capacity reduces. We done a series of analyses and then found that the reason why we reduce the capacity is because the lever arm of each of the wall reduces, and therefore the moment resistance reduces, and that effectively changes the efficiency of the wall system. The connector, what we used is a stainless steel connector. Worked beautifully in the test, but we identified two problems. One is the behavior of the connector is very difficult to predict. So if you want to predict the building behavior in the future, it's going to be pretty tough. And the second one is because the stainless steel, it costs you more. The welding it requires some special welders to do the welding, so it's not as cheap as using a steel connector, if you like. So the advancement, what we thought we need to come up with is to obviously improve the cost effectiveness. And we also wanted to address this floor diaphragm interaction that in the press building we were able to isolate it, but that's not ideal in a real building. And then the press building was subjected to a pseudodynamic testing, so the radiation damping, which is typically expected when a structure rocks on a foundation, was not accounted. And obviously we wanted to advance the analysis and design capabilities as well. So let me just talk about the PreWEC system in detail that Susie introduced. So the PreWEC system essentially uses a precast wall with two end columns on either side. So what you see here on the ends are the end columns, and all three components are post-tension to the foundation in this case. And the advantage here is that you place the connectors between the column and the wall panel. There are several benefits to this system, which I will explain in a moment. But I also want to emphasize here that by placing this joint close to the edge of the wall, essentially what you're doing is you're actually increasing the lever arm of the wall, and therefore the efficiency of the system goes up. Now, if you look at the PreWEC, once you have a concept like that, you can actually configure it in multiple different ways. So you see some options here. In the first case, I'm looking at putting two wall panels in between two end columns. If you want, you can place the intermediate column as well, and that provides some additional benefits, which I will talk about it. Or you could have multiple wall panels here as well. In the current research, we are also considering an option where we are looking at placing columns on the side, and that provides further increase to the wall length, and depending on how you want to transfer the gravity load to the system, this option is also considered to be beneficial. We have also analytically looked at this PreWEC concept for a core wall structure, if you like, but we, in the near future, we are not intending to do this investigation through experiment, but this will be something that in the future we will be interested in doing. Now, let's take a look at some of the benefits. So as I demonstrated to you, it's definitely more versatile. So what we are doing here is we actually separating different things. So the damper is placed somewhere here between the end columns and the wall panel. The stiffness is largely controlled by the unbonded post-tensioning here, which is allows you to separate the strength component from the stiffness term. And then when you use this system with the floor diaphragm, what you can do is you can actually transfer the gravity weight or connect the flow system either to the PreWEC bore, or you could do it to the gravity column. So it also opens up another opportunity for you to transfer the load differently. So it's versatile. It maximizes the lever arm, which I explained to you. It facilitates transfer of gravity loads through the wall or columns, I noted. And then the connectors are now exposed. Therefore, they can be easily replaced. And typically what we're expecting is that you design your post-tension such that for service level loads, the post-tension will be sufficient for the walls to resist the load, and therefore after an earthquake, while the building is functional, you can replace the connector so that you can get the building ready for the next event if connectors are required to be replaced. Now, I talked about putting the intermediate columns between wall panel, and there's a huge advantage in putting that column. One, the column can be used to transfer the gravity load, and the second thing I would emphasize is that when you place a column and place the connector between the column and the wall panel, what you find is that the column doesn't uplift, and therefore any of the energy dissipating element that you place in will be subjected to large tensile strains but small compression strains. So if you want to use a rebar like what I've shown here, the advantage is that you won't experience buckling problem because the compressive strains are limited in comparison to tensile strains. Now, you could design the connectors in a number of ways, and there are some documents available at the NEES website. And we've gone through an investigation where we looked at various connections. There are three variables you will iterate. One is the amount of force that you want to have in the connector, the deformation capacity, and the maximum strain that you're going to be permitting. And based on these three variables, you can go through different designs and then come up with what would satisfy for your particular need. And in this case, what we ended up doing was we ended up coming up with what we call a oval-shaped steel plate connector. And as shown here, it requires very minimum welding, and this is done outside on the surface where you will use an embedded plate into the column as well as in the precast wall, and this connector can be replaced. And on the right side here, you see the force displacement response of a system, and you could see we subject this connector to more tensile or one direction displacement than the other. We are assuming in this case that we're going to be connecting this between a column and a wall panel. The concept test has been completed. This was done earlier as part of an investigation funded by NSF and the National Science Council of Taiwan through this international program. What we did was we did a series of tests at University of Minnesota as part of a T-wall project that Kathy French, myself, and Susie were involved, where we did a series of T-walls as well as 3 rectangular walls. The rectangular walls RWN, I've shown the cross-section here, essentially provided a reference wall for most of the studies at the University of Minnesota. So what we did was we took that reference wall as a reference for this particular study, and we came up with an equivalent PreWEC system. So the variables that was used to limit here is that the end-to-end for the whole system, the length was kept constant. So from the end of the column to the other end of the column in a PreWEC was equal to the RWN length. The thickness was maintained to be the same. And then we redesigned, based on the post-tensioning, the connectors to match or exceed the capacity of the RWN. So as I noted earlier, one of the major concerns was that we want to make this post-tension precast wall system to be as efficient as the RWN so that you can replace that easily without increasing the dimensions of the wall. And here's a view showing the PreWEC system that we designed, and you can see there were the wall height was 260 inches. The loading was applied at 20 feet, and the length of the wall was 90 inch, same as the RWN that you show in the picture on the right side. And here's the construction of the so the PreWEC wall panel, and you can see the amount of reinforcement is not very significant. We do have confinement placed in the corners, and we were suspecting that we were putting too much reinforcement. We were following the court recommendation, and then we did use this embedded plate to help us weld the connectors to this particular wall panel. Now, here's a video of the test. I don't know if it's going to work. It is working on my computer. If you can't see it, there's a web or the YouTube address I've included, or go to YouTube and type PreWEC, and you will see it. So what you see here is essentially a wall being subjected to a cyclic back and forth motion, and we subjected the wall to a progressively increasing intensity of displacements, and then eventually move this all the way to 3.5% drift. So it essentially rocks back and forth on the foundation and provide the resistance that you're looking for. So here's the second video, and this video shows a close-up near the base of the wall. The yellow color shows the column. So in this case, actually, we used a steel tube and then filled with concrete. So we were able to weld the connector, as you see here, to the reference column as well as to the concrete wall panel. And here's the embedded plate. And you could see when it rocks, essentially it deforms the connector in the in-plane direction. So by allowing the ore connector to deform, you are able to dissipate the energy in this case. So if you go and look at the force displacement response that we obtain, so let me just compare the damage real quickly. So this is the PreWEC after the test at 3%, and you could see in this region there are some surface crack showed up. It's essentially within the confined region of the, within the cover concrete, so the confined region was still intact. You could see some permanent deformation here, which is mainly due to this some bending taking place to this plate, and that's partly because we were putting a fairly high amount of initial post-tensioning, which is typically not required, but we were exercising to the maximum to see if we would have any negative impact due to that. And then this one shows the connector a little more closely. Now at 3%, what you see on the right-hand side is a RWN, and you can see the extensive damage to that wall panel. And in this case, the wall panel was designed without any splices because that was a reference wall in this case. So the plastic hinge was forming, and eventually we experienced some outer plane buckling to this wall. But I think without going into the buckling issue, you could just compare the extent of damage between the reinforced concrete walls to the PreWEC system. So here's the force displacement response of the system. So what you see here on the left is what we recorded for PreWEC, and as I said, it went all the way to 3% drift, whereas RWN is shown in green on the top right. And then if you compare the two envelopes, and you could see the PreWEC actually provided higher resistance because of the amount of post-tensioning we used. And then in this case, we actually exceeded the capacity of RWN as well. So the RWN responded fairly well until 2.5% drift, and the negative slope that you see here is primarily because of the outer plane buckling taking place. And whereas the PreWEC continued to go all the way to 3% drift. And at that point, we actually experienced some fracture of the connectors because of the fatigue taking place to the connectors. So I'm going to show you some of the results from that particular test. So one is what happened to the post-tensioning tendon. So the post-tensioning tendon, because it was research, we targeted to have the post-tensioning yield at 2%. And so when we reached a drift of 2%, you could see the post-tensioning going to yield, and there was some permanent deformation to the wall panel. And then eventually we ended up reducing the post-tensioning by about 10%, which is not significant compared to what you would see in other situations. And always you can design the post-tension to have not yield all the way to 3% or 3.5% drift if you choose to do it. ITG that Susie mentioned does require us to limit the post-tension to different drift level, and so we followed in this particular case what the ITG was recommending. Now on the right side is a figure that Susie has already showed. It's essentially showing the uplift of the wall right at the interface here. So the point I want you to understand is when you uplift, I think it's a common observations that people make, you see a fairly large uplift at the base of the wall, which is essentially a concentration of all of the cracks likely to take place further above. And then you look at the concentration of crack and then say, well, for that uplift, now we're going to have a problem with the flow because the flow has to experience that much uplift as well, or the differential movement between the wall panel and the flow system. Now, if you look at the reinforced concrete wall, the reinforced concrete wall also cracks, develops series of flexural cracks. So you could sum up all of the cracks and look at, okay, how much uplift I'm going to have for the reinforced concrete wall. And what you find is that the reinforced concrete wall actually will come out to be slightly higher than a PreWEC or post-tension, unbonded post-tension walls. So the reason being you develop series of crack and you don't necessarily close all of the cracks properly, so therefore you end up having slightly longer or larger elongation at the floor level. So that's what you're seeing in this figure, where if you look at what PreWEC is doing is a very clean uplift back and forth. So this is what you're seeing as the drift increases. We're looking at the deformation, if you like, what's happening at the first floor level. And so it lifts up about 2 inches. Now, this blue line is what we actually picked up for RWN if you look at the total elongation of the wall at the first floor level. So it essentially tells you for a given drift, your blue line is going to give you much larger drift. It's almost, in some cases, 50% more. Now, Susie mentioned about this corrected curve. remember the PreWEC has a slightly shorter wall length than the entire length of the RWN because we are putting in columns at in this particular case. So if you correct for the actual, so what the purple line does is what is the elongation or the uplift of the RWN at the edge of or the end of the PreWEC wall, then you can correct for the dimension, and then what you find is that still it comes out to be slightly higher, but in both cases, both of them are greater, provide you greater uplift than the post-tension wall. So I think that the one thing to realize is this uplift is real, and it's going to take place no matter what type of system that you use. I think the precast system with the post-tension highlights this uplift, and therefore, the designers and owners tend to be more concerned about it. But I think the reality is that if you're designing regular reinforced concrete systems with a rigid floor diaphragm, we should be able to look at that option for PreWEC or other systems as well. Now, this figure shows the neutral axis depth as well as concrete strain demand, and what you see here is that this is very typical. So you see a trilinear approximation that we typically use for design as well as for analysis, simplified analysis, and which you can see that's showing a similar trend compared to what we are picking up from the experiments for the PreWEC system. And we did place a number of concrete strain gauges in at the wall toes, if you like, and we did get pretty good strain data. And this one shows, in one case, we did record up to close to 18,000 microstrain. So the strain demand is something we were able to capture and then correlate that to the amount of confinement one would need in that region. Now, going back to the connector deformation, so this is the connector at 3% drift, what you see on the right. And on the left side, if you measure the vertical deformation between your wall panel and the PreWEC column, and this is what you pick up. And again, I will emphasize that it lifts off in one direction where the wall panel lifts. It's going to create a larger deformation, but in compression, you actually experience a smaller compression, and therefore this opens up more opportunities for innovative connectors than what we were able to do in the past. Now, one thing that we have done with the PreWEC test is that the ITG 5.1 and 5.2, that was an effort that it was a requirement or request came from the PCI. Eventually, ACI took over and came up with this document. And this document spells out what you would need if you're going to develop a new post-tension system. You need to meet, X, Y, and Z. So with the PreWEC system, what we have done is we actually gone through the document and made sure we met everything. So in other words, we have achieved what the ITG is required, so therefore you can actually use this system in practice. There's one piece that we have not addressed, that the ITG 5.1 requires that we do at least 2 test modules, and we have so far done only 1 test module. But in the current research, which I will talk about it next, we are planning to do a series of PreWEC systems. So obviously, by the time we're done with research, and we'll pay attention to it, and then make sure that the ITG requirements are met, you will have all of the information necessary to satisfy the code requirements. So therefore, you can use it in practice. So here, what I wanted to highlight is that most of the other requirements within ITG, which talks about the scaling issue and what type of test one should run, and there are some expectation for the drift limit and the strength degradation. And if you focus on the right column, it tells you what we found. So in all cases, what we found was the expectation from the system was that we were able to meet all of the requirements except for the first one, which requires multiple test units. Now, in this particular slide, you can see the relative energy dissipation required in ITG 5.1 is about 12.5%. And for this PreWEC system that we tested, if you focus on the blue line, at design drift, we were able to get close to 18% damping. And one of the beauty of this external connector is that you can increase the thickness or you can increase the number of them if you want to increase the amount of energy dissipation. And therefore, it's easier to manipulate the system for your need. Okay, so I'm going to move on to So why are we doing more research, and what is this NEES project? We call it the NEES Rocking Wall Project. And there's what advancements are we going to be doing? And I want to just touch on that as my last topic here. So the current research focuses on a few different things, and I will go through one by one. One is the anchorage of unbonded post-tensioning tendons. I think there are still concerns when we use unbonded post-tension anchored to the ends. Can they be relied upon in earthquake situations? Contribution of different damping components, the other component that we are focusing on. We are also addressing the resiliency of buildings because what we have done in the past is that we have focused on developing self-centering systems. These are systems designed to resist earthquake loads, and therefore we are now in the phase where we are making sure these systems can self-center. I think the argument that we're suggesting here is that even though if your system can self-center, the building may not self-center. And that's the portion that we will be looking into this particular study. And again, I'll go into with a little more details. And then the connection between floors and rocking wall is something that I touched on, and we are definitely will be looking into it. And then I won't have time to get into the analysis aspect as well as the design guideline, except to say that we actually do have a design document for PreWEC system that you could use, if you choose to design a PreWEC system for your need. So this particular research is being done in collaboration with two international groups. One is the group at University of Auckland in New Zealand, and they are looking at this damping issues, essentially using a mass shaker where they are rocking individual walls to get a handle on some of the damping aspect, and then sharing the data with us, and we're sharing our information with them to see how well we can understand how we can improve the behavior. Rick Henry is the faculty member at University of Auckland in charge of this program, along with his colleagues and students. The second collaboration is with the E-Defense group in Japan. The E-Defense has completed what they call a twin building test, and we are fortunate to be part of that research as well, where they tested two buildings side by side. What I've shown on the right side here is a precast concrete wall, and this particular wall, as well as the wall on the back side, was designed using a system that Susie mentioned, where you have an unbonded post-tension as well as some energy dissipating rebar buried between the wall panel and the foundation. Now, one thing that I would highlight is, so this system, this building actually performed better than the equivalent reinforced concrete building, which was designed and placed right next to it, and it formed plastic hinges and experienced some problems with the wall failure, which is, I don't have time to go into that particular topic. But what we are doing is we are actually utilizing data from this building to help us design our test unit so that it will benefit us as well as the E-Defense group. Now, one of the obvious problems which we suspected and included in our project that we are hoping to investigate is this outrigger effect that Susie explained. So when you have a wall panel rocking, so if you just focus on the in-plane rocking of this wall, the floor diaphragm and the gravity column or the seismic column, what you place here, is going to be participating in, in the force resistance. So if this floor diaphragm creates the framing action between your floor, your wall panel, as well as the gravity system or seismic column, what's going to be happening is that for in-plane loading, you're going to see forces being increased in the gravity columns as well as, if you have a seismic column, for example. So the problem being, even though, I think if you go back and look at what happened in past earthquake, the gravity system has caused problem where we, I think, found in Northridge that the displacement compatibility was an issue. Now you create the displacement compatibility, let them go for the ride, but you're going to create some framing action. Depending on how the boundary conditions are established, you could be transferring fairly high or increased large axial force, compression, and tension due to this outrigger effect in these columns. That's exactly what happened in this building, where these columns, these corner columns, I've included some pictures showing because of the high axial load increase, started to damage the corner columns much more severely than some of the actual seismic resistant system. In this case, it's a in-plane wall. This particular building was subjected to three-dimensional ground motion. So in terms of doing some analysis, it's much more complex, but we are tackling this in terms of understanding the three-dimensional aspect using this building as well as the data from this test. So with that, let me just show the different pieces that we are undertaking, and based on, you may have some interest, and if you have interest, we're looking for input from you. If you think that we have to perhaps consider including some additional variable, or for example, if you think that whatever we are testing will be useful to you, we encourage you to be in touch with us, and we'll make sure that you get the benefits from the project as well. Now, the first component I'm going to talk about is the anchorage of the PT tendons, and this is the work is the work is being done by a team at the University of Minnesota at Duluth. Professor Eric Musulman is the person in charge, faculty person in charge, and he has got two students working with him. Essentially, what we are looking at is we are looking at monotonic testing of individual strands as well as multi-strand, and then we are repeating those tests under cyclic loading as well. There have been some concerns raised. I think the initial study was completed by Gino Crama at University of Notre Dame, where he published papers indicating at the time we were writing the proposal that the unbonded post-tensioning anchorage may be a concern that needs to be looked at. So we are aware of what Gene is doing. We are collaborating with him, and then we are also collaborating and discussing with the manufacturers of anchorage to see we could show that these tendons can be tested and shown to be adequate. So the industry has identified this as, in some cases, a problem, and they are manufacturing, or they're coming up with some new wedges that they believe will help us resolve this issue. So in some of the tests, we are using new wedges that goes into these anchor ends, and these are not specially manufactured. These will be available for use in design practice, which is something we are making sure that it will be available to all of you. The monotonic test right now shows that we are breaking strands. Typically, it breaks at the end in the anchor region, and the capacity that we are seeing is it reaches about 96–97% of the ultimate capacity. And we have tested the monostrands with couplers in between the ends and without couplers, and the couplers doesn't seem to have any influence. We then ran a series of cyclic tests, and you can see on the x-axis where we are looking at different variables here, and then that provides the different range that we are cycling it. The one on the right is where the severe fatigue load was applied, and you could see that they are also still breaking at 97–98% of the ultimate capacity. This shows a test series that we are doing with the multi-strand test setup, where we're using the standard, which you typically buy from a vendor, and then we're also using a new wedge that is being manufactured or recently manufactured and will be available for use if you chose to use the new wedge. And we're expecting that in terms of achieving larger strain capacity in these strands, perhaps the new wedges would be more dependable. And the tests have not been completed, but once we complete, we'll be happy to share the data. So this one shows the test setup that we have been using in terms of doing the multi-strand test. The left side, you see the actual test setup, and the right side show what we do, a typical pull test. And we also looked at rotating one end to create some twist to the strands, as it could potentially happen in a multi-story building, to see if that would cause any problem, and so far we found that the rotation doesn't seem to have any effect. This one shows the multi-strand test, how we are breaking, and you could see that the break is, on average, is about 95%, so it's slightly less than what you see for the individual strand, but our hope is to get these numbers to a higher level and then higher inelastic strain limit, so that we will not have any problem using post-tensioning, unbonded post-tensioning in future structures. The second point I mentioned is that in the past we have paid attention to the viscous damping as well as the hysteretic damping. The hysteretic damping typically in these systems come from some kind of an energy dissipation element like the O connector that we are using. Now, one thing that we have not taken into account is the radiation damping. How do we quantify and how do we bring into the design table? So if you look at it, the question that we are trying to answer is, do we need to have all three damping components for the system to work in a seismic situation? And then if you say the viscous damping and the radiation damping is sufficient, maybe there may be cases where hysteretic damping is maybe needed. So when do we bring that hysteretic damping into the picture? And I want to emphasize one thing, that these three damping, they contribute to the system response. So in a sense, one damping can influence how the other damping component is going to be working, in terms of helping the lateral force resisting system responding to the earthquake load. So to address this particular case, what we are doing is we are doing a series of shake table tests, and this shake table test is being done at the NEES facility at UNR. We're using one single shake table where we place a rocking wall connected with the link beam, if you like, to a inertia mass placed outside. And we're looking at different variables in this series of tests. So we are looking at individual walls rocking without any hysteretic damping, and then we're also looking at bringing PreWEC with different damping elements or different amount of hysteretic damping, and then going through the same input motion. We're looking at initial post-tensioning as one variable. And then we will also be looking at, it can be increase or modify or have control over the radiation damping by means of some other product that being used at the interface. I mean, that's something that we are still exploring to see if that would be a possibility. But in any case, we have only done 2 tests so far, and then we are going to be testing a series of walls in February or March of next year that we are getting ready to do that now, doing the design right now. The test that we completed is in the last test. There are 2 tests have been done. The second test was completed last summer, and I just want you to see some of the earthquake motion that we are using. The intensity is very similar to what Susie introduced. We go through a 4-level intensity of motion, EQ3 being the design level shaking, and then EQ4, we have multiple of them. We use the Chile earthquake, the Northridge, the Takatori event that was primarily used for the testing of the E-Defense building. And what I want to show here is 2 things. The response of the system so far has been very good. I mean, we are picking up large displacements, so you can see when we run to one of the earthquake motion at 4D, EQ4D, we were seeing drift as high as 4.4. So when you have no hysteretic energy dissipation, it's not surprising to see that the drift is definitely getting higher. Now, in all cases, if you look at the residual displacement at the end of shaking, they're very small, so they do recenter pretty good. And here is one of the last tests. But one thing I want you to focus here is that how long these walls respond. The duration is, you're going to see it in a scaled system. So let me see if I'll run it a couple of times so you can see and maybe hear if I turn the volume up. So the rocking takes place actually for a longer duration. If you had hysteretic damping, probably we would have dissipated it much faster. So because of the scaling, the duration of the time it took to run the test appears to be short, but if you use the scale to figure out what will translate to a full scale, that shaking lasts more than a minute. So the wall goes back and forth in terms of, dissipating the motion, relies primarily on the radiation damping. So here's how the response looked like for the last test I've shown you. So once it hit the maximum value, it goes through the decay in a slightly different manner than what you would see for a system with hysteretic damping. But then in this case, even at test 18, you could see the amount of residual displacement that we ended up getting for this wall system. Here is the wall maximum lateral displacement for various tests, with the blue showing the last test, which was the test 18. And you could see some of the damage to the wall at the end of the test. So the blue line that you see here is essentially some shrinkage crack that we identified and marked before the test. And after that, see this, the test 18, you could see there's no damage to the wall that you see here. So the damage is minimized, the wall recenter, the rocking lasted longer, but other than that, everything was worked out perfectly. In the first wall test, what happened was, we did put the steel armor that Susie was talking about in the corners here. What we found was that the cover concrete actually gets damaged, and which affects the performance of the wall as well as, so the corner of that region, the corner of that wall was somewhat more damaged than what you see here. So in this particular test, what we did was we isolated, we put a soft foam, if you like, right underneath the cover concrete, and we allow all the transfer of forces directly through the core concrete. Actually, that helps us to even prevent any damage to the cover concrete, and then the wall looks pretty normal after the earthquake. Moving on to the next topic is where I talked about system versus building resiliency. So if you take a PreWEC, and this was the PreWEC that was modeled by Rick Henry, where he took a PreWEC system response, and he was able to match what we tested at EERI and came up with the force displacement. So we're showing one cycle. You take the wall to a 3% drift, and then bring it back and see you came up with 0.5% residual drift, if you like. Now, you have a series of floors here, and these floors are rigidly connected to the columns. Assume these are gravity columns at the ends, but you're going to be now resisting the floor deformation, and therefore you're going to be creating axial loads in the column, and therefore a couple that's going to help resist more forces. Now, if you quantify what that amount is, and this is what you're going to be seeing. So in this particular case, we found two things. We pick up 40% increase in resistance. So if you're a designer, one option is you can possibly take this into account, even though design codes doesn't allow you to do it right at this stage. But the second concerning problem is that the self-centering of the whole system. Now you can see that self-centering of the PreWEC has been compromised. It's true for any other system. If you rely on a system like that, and if you rigidly connect the different pieces together, what you're going to see is that it's not going to recenter as much as you hoped based on your system, based on your response of the earthquake resisting elements. So unless you account for this in the design, even though you're designing or you're starting to build a new concept and hoping the building to recenter after the earthquake, you may not achieve that in real life. So that's this other piece that we are trying to address in this study. So we're looking at three different things. One is to see what would happen if you rigidly connect the floor to the PreWEC system. And in this case, we are going to allow the floors to deform, and based on the analysis, we are expecting some damage to the zone right adjacent to the wall panel. But we know the extent of damage, and we know we can repair it. They're not very, they are yielding the reinforcement in the slab. Nothing more than that. So hopefully we can repair it if the building can recenter, and that's something we need to pay attention to. So therefore, our option one of the options is to allow a rigid connection and then figure out how much is the outrigger effect. How do we address this? Can we still make sure the building can recenter? The second option is to isolate it so that you completely isolate it. And as I mentioned earlier, I think the PreWEC provides an opportunity where you can actually directly connect the flow diaphragm gravity loads through the PreWEC columns, but then you transfer the inertia through some other connectors, which needs to only transfer the shear directly to the wall of the PreWEC system. And so that's something that we are currently investigating to see if we can come up with that detail. So if we can come up with those two options, you essentially have two ways to build this concept. The third option that we are trying to exercise is somewhere in between the two, where we provide some partial connection, which, if Susie wants to discuss that point further from a design point of view, we could talk about that at the end. I see some question coming up. I'll let Susie read, and then we'll come back and answer them. So if you have questions, send them through the chat, and we'll get to them after the presentation, which I'm almost done. So here is a prototype building that Susie designed. So they are 30 feet for each bay length, if you like. So this side is about 80 feet long. So for the other phase of the project, what we are doing is we are going to be testing a building PreWEC system with a flow diaphragm. In the flow diaphragm, we are going to be providing different types of connection to see how we can bring in the interaction, how do we quantify, and can we actually make sure the actual building will recenter even though the PreWEC can recenter. The series of tests in this case is going to be done at the NEES facility at MAST, or University of Minnesota. Professor Kathy French is the person in charge of that test. And so this is what Kathy and her team is going through. Essentially what we are doing here is that we have a PreWEC with a flow diaphragm, and we can't afford to build a test unit with 6 floors. So what we have gone through different iterations, and then eventually what we are going towards is a building that will have 1 flow diaphragm, and then we will have the second floor is not going to be modeled, but we're going to have a beam, which we call it a mega beam, which is going to provide equivalent resistance that you would expect from all 5 floors. So we designed these beams to have adequate resistance so that the columns in this case will experience the same amount of axial load effects, and therefore we can capture the outrigger effect, and then we can also look at the flow performance using this 1 flow diaphragm. So that's the direction we are heading in terms of our first test unit at MAST. This shows the test setup. If you're not familiar with the MAST, they essentially have a crosshead supported by 8 actuators, and we are going to be placing this test unit underneath it, where we are going to be exercising to look at these various the outrigger effect and the interaction between the flow diaphragm, gravity system, as well as the self-centering element here. With that, I think we are pretty much on time in terms of wrapping this presentation. So let me just summarize a few points that we emphasize. I think the PreWEC is a versatile system that has shown to meet the ITG requirement, and this can be implemented in practice. As I said, you need to have one other data point. By March, we should have some PreWEC tested on the shake table, so you will have, and we will make sure that we meet the ITG requirements, so therefore you don't have to invest to do tests. Issues related to flow uplift. I think it's clear that based on some of the actual earthquake damage, it's an issue that needs to be addressed. But I think these issues are not confined to just precast system alone or self-centering system alone. It's a problem for any buildings that needs to be looked at, and I know there are some other NEES projects looking at diaphragm issues as well. The anchorage of unbonded PT needs further investigation, and we are definitely addressing that. And we will be doing more testing in the coming months, and if anyone is interested, we'll be happy to inform you of the outcome of that research. And then in addition, we are going to be looking at the impact of radiation damping. That is going to be done using the upcoming shake table test, and the interaction of floor, wall, gravity system that we will study with the mass test that's coming up. Hopefully next summer is what we are targeting to have our first test unit built, and then the testing will follow soon afterwards. So with that, if there are questions, I'll give it back to you, Jared. If we can answer questions, we can take care of that too. Susie, unless you want to add anything, please feel free to do so.
No, I think that was great. Very clear.
Okay, well, I'll start going through some of the questions we have in the list here. This question is for Sri. Is the outrigger effect frame behavior from interaction with floor slabs and gravity columns common to and have similar effects in both PreWEC and cast-in-place systems? Or is the effect more significant, for example, in the form of higher axial loads in the columns from E-defense results in one system rather than the other?
No, I think it's true for any system. I think it's how you connect your floor diaphragm to the seismic resisting, seismic force resisting elements, and how it's supported at the gravity column. So I don't think it's related to it's a precast problem. I think it's a problem for any building. In the E-defense test, the reinforced concrete building actually did not, I think what I recall is it did not see that much column damage. That's partly because the reinforced concrete wall started to fail earlier on. So the wall was sliding at the base, so I don't think we had the same effect in the reinforced concrete building. But I think that I believe the problem is not confined to precast system. It's a problem for any buildings, and I think Susie, from a design point of view, should say something here as well.
Yeah, I would really like to add something. First thing is that although my friends at PCI won't want me to say this, you can put a cast-in-place slab in a precast PreWEC wall, or you could put a cast-in-place wall in a precast floor system. So when we talk about a precast building versus a cast-in-place building, I think we need to separate that in terms of the behavior. Sri talked about the uplift of the end of the wall being actually greater for a cast-in-place wall than a jointed rocking wall. So I think that's something that's real. Now, as far as the cast-in-place slab system versus a precast slab system, it has everything to do with the connections, and that's a big part of my participation in this MAST research. The first MAST test is actually with a cast-in-place post-tension slab with the PreWEC wall, so that we can maximize the outrigger effect and basically make it as stiff a connection to the PreWEC wall as possible. And then we're going to go the other extreme and do the minimal stiffness in terms of flexural outrigger effect stiffness. Hopefully that makes sense.
Yeah.
Okay, have another question here. I noted all tests were performed using single isolated panels. How will the effect on wall panel behavior be affected by spandrel panel framing to the wall pier?
Susie, you wanted to...
You're going to make me answer that one too, aren't you?
No, I could talk about, one related point here is the outer plane issue. The walls in real building can be subjected to outer plane motion. So even though we are testing individual walls with the in-plane loading, there's a genuine question in terms of how well it's going to work in the outer plane direction or two-component earthquake motion. And if you look at the E-defense building test, that was the other useful information for us to observe, that the building or the wall panels were actually subjected to bidirectional components. So instead of the wall panel rocking from one toe to the other, it actually rocked essentially from corner to corner. The outcome remained the same, and the same thing applies to cast-in-place wall as well. So we are not focusing right now on the multiple direction input motion in our study, but we are doing analyses to understand the E-defense building response, and at least we will look at that phenomena using their data and our analytical models. But the spandrel is what I was hoping that, Susie, you could answer. If I don't think I'm getting...
Yeah, I don't know. The spandrel question specifically, I think, is true with any attachment to this PreWEC wall, or any wall for that matter, is you have to pay attention to the deformation compatibility or deformation motions that you're going to have. Because these are jointed systems, because they're built separately and attached together, you really have to look hard at how the connections are put together. Precasters do that typically with cladding panels, with cladding thought process that goes into cladding attachments to a building is very similar to the thought process one needs to go through in designing and detailing spandrels and floor systems and everything else. We'd like to add something though to 3's comment about out-of-plane motion. Since all of the buildings that I design could get hit in any direction, that part is really important to us. And if you look, I don't know, can you go back to my screen, Jared?
Do you want to share yours?
Yeah.
Okay, I'll pass you the ball. There you go.
And hopefully you're seeing my precast hybrid wall. Oops, maybe in a minute. Precast hybrid wall 5.2 design guidelines.
Mm-hmm. Yep.
There's 2 pictures there, and if you think about how these behave, actually in the ITG document, they show a detail here where it has the energy dissipation bars pulled into the middle. In the building we're implementing in California, we actually did not do that, mostly because of the out-of-plane loads. We pulled those bars out to the end. We actually have another set of bars that's in a little bit more, so we have to deal with the out-of-plane motion with these few connectors that go between floors. That was not done in the PRESS research. Those pictures that I showed you that had just the rebar at the end of the walls up here, and they actually had no rebar at the bottom here. So when there's out-of-plane motion, you'd have to create a different kind of out-of-plane connection here. When we actually invented a base connection for Stancrete. Stancrete has a hollow core wall system that has a base connection where this was a major issue as well. So as engineers are implementing these systems, it's really important to pay attention to that out-of-plane motion or out-of-plane connection, which is very different than what you have in a cast-in-place system. But you don't need to detail it like a cast-in-place system. You just need to pay attention to it. Okay? Can I give you the ball back?
Yep. Okay. Let's see what other questions we have here. Here's a question. In both options, I mean option 1 and option 2 of page 44, both floors should be assigned as rigid. The only difference is between the connection with the wall. Is that right?
Yeah, that is correct. So the option in one option, we are allowing the floor to deform, even though they are rigidly connected. In one case, we are allowing the floor to deform by rigidly connecting to the precast wall. In the second option, we will be transferring the gravity load through the PreWEC columns. So the PreWEC columns, as I shown earlier, doesn't go through a lot of large deformations. So therefore, they remain, without any significant flexural deformations, but they rigidly connected in that sense. It will be transferring inertia forces to the wall panel.
Can I add something to that too, Sri?
Yeah,
that the whole question about rigid diaphragms, I'm assuming this question came from a designer, that is independent of the connection to the wall. So if you have a precast floor system that is jointed as well, then you need to model the behavior of that type of floor system too, which is not in the code right now, but that's another NSF-sponsored research program that is actually being done by a consortium of researchers, and it's the National Science Foundation and PCI sponsored. So if you need information on that, please contact Roger Becker at PCI. But that will tell you how to model a floor slab as something other than just rigid.
Okay, I have another question. What software are you using in your models, and are you using fiber elements or shell elements to model the walls?
So we have used several different techniques. So for example, we've used, so some of the detailed finite element models that you've seen was done using Abacus, where we use shell elements. We've used Romoko for some just essentially representing the response with the frame elements, and therefore we were able to subject that model to ground motions. And then we also have developed a simplified analysis procedure where we start with a trilinear assumption for the neutral axis depth, and from which you could solve most of your design variable, which is something you can use use in Excel or something. But one useful feature of the analysis is that it will give you the force displacement response that that you're looking for in terms of pushover analysis. So depending on the extent of details that you need, you could use any type of software.
Okay, another question. I missed the first part of the presentation, so I might have missed your coverage of this issue, but how much sliding due to shear takes place at the base, and how is this physically restrained?
The answer is 0. Therefore, it's not. The compression force, that's part of your design process, and it's in the ITG 5.2 document. Although I will tell you, as we implement the ITG 5.2 document, that part of it is extremely conservative and a little bit excessive. I'm working on getting that changed. But the concept is that you have a compression force at the your panel that then has a friction, creates a frictional resistance that prevents sliding. And you have to make sure it doesn't slide. That's part of the design process.
So if I may add to that, so in the PreWEC test that we completed, in the jointed wall test, we always try to measure the slip at the base, and as Susie said, the slip is not there because of high post tensioning. Now, we also typically place this wall inside a pocket. So typically you will have a pocket on the foundation. We drop the wall in, and then you grout the interface between the wall panel and the foundation block, if you like. And typically we bring this grout slightly above the wall panel. So in essence, these wall panels are sitting in a pocket, so there's no room for it to even slide, even if it's going to slide. So so far we have not found any sliding from the test.
I'm going to just point out the reality of real life is when you have perimeter wall panels that are continuous around your building, there is no pocket. So we really, the prevention of the sliding is really an important step in the design. But again, it's capacity design.
Yeah.
So Free's right with the details for the test, but in a building, that's a part of your design criteria. But we do that for the maximum capacity of the wall, not just for the design forces.
Okay, here's another question. Is it possible to have rounded edges to avoid the problem of surface cracking instead of armor?
Rounded edges.
Yeah, I think so, like a chamfer or something like that. I think that would be a great idea. This is what's always been one of my disagreements with the research world is the armor, well, it is fine. What it does is it just moves the point where something falls. And if we can do that by making it stronger, that's fine. But the other option is to eliminate, which is what Sri's doing in the test with the styrofoam, and that would probably work the same way with some sort of chamfer at the base of the wall as well. But you need to make sure that your chamfer, you still have to have cover on your rebar, so the chamfer is a little bit more difficult to implement.
So just to follow up on that, so we are planning to do, and at least we will do some test without armor, and we will see if we can address this cover issue by chamfer or something to minimize the problem. And then, do you want to read the other questions? I think I see one above and one below that, Jared.
Let's see here. I see one asking, the system seems to rely on a relatively limited number of elements. Are there any related robustness or redundancy concerns?
That's mine, right, Sri?
Yeah.
The answer to that is it's just like any other system. Yes, you have to consider robustness. In the building that we're doing in the Bay Area, it's very robust because we have the entire perimeter is shear walls, and every party wall is a shear wall. So we have very short spans on our diaphragm, and we have a lot of vertical systems. Other buildings might not be the same way, and there's no need for that, but those are addressed the same way as any other building system.
Okay, I think we have time for maybe one or two more questions. Let's see here. How realistic is application of these hybrid walls in real life? It will need concrete and steel team to work together and probably cost more.
No, we're doing a total precast system right now, so there's no steel associated with our system other than connections, typical floor diaphragm connections. If we were to do a PreWEC wall, we would probably be working with a precaster and have precast columns, not steel columns, but it could be either way.
Yeah.
But because of the need to stick with one producer, I think have it all precast. But welded connections are very typical for precast.
Yeah, that's what I was going to say. I think the in the PreWEC test we actually used I think I mentioned a steel tube filled with concrete because we were doing a half scale and it's hard to build a column of that small size. And you could easily replace that with any other member. It could be a concrete element. It could be just a steel tube without concrete. You just need to provide some reference member there. It doesn't have to be steel. So you could easily build all of it using concrete or precast members.
Okay. I believe you mentioned that there were several rocking wall structures in Christchurch that were subjected to earthquakes. Do you have any data on the non-structural performance of these structures or have any floor acceleration data from the structures?
What we know is the building was located within, for those who are not familiar with Christchurch, that the February Christchurch event caused significant damage to buildings. The epicenter was very close to the central business district, and I was fortunate enough to represent the EERI team to go and visit the buildings, and my focus was mainly within the central business district, which was cordoned off. But this particular building I actually did not visit, was just outside, I believe was just outside the central business district. And because the building performed extremely well, the building was functional after the earthquake. There wasn't much talked about this building immediately after the event. As you may know, Christchurch has going through a series of demolition, and they are expecting to have about 75 to 80% of the building demolished and rebuilt because of the damage experienced to most of the other building. This particular building, and along with another hospital building just outside the central business district, have been recently talked quite a bit about because the second building was on isolation, and this particular precast building used this unbonded post-tension concept. And I think my understanding is that both buildings are functional, and there wasn't any serious damage to both of these buildings.
There is a test report reporting on both those buildings, and yes. I think that's also posted on your website, right, Jared?
Right. Yeah.
Yes.
So there's a Royal Commission of New Zealand has a website with a lot of the information, and there's a report dedicated to these what they call a special building, and I will have that particular reference included in our supplementary material that Jared is going to place in a folder for participant to access.
Yeah, after the webinar is over, within 24 hours or so, I'll put a recording of the webinar as well as Sri's materials that he sent into the page at the link under webinar recording will be available that you can see now on your screen. I also want to point out that we do offer PDHs for attending this webinar. That link is there. You can go and register for that. I think it's 3:30 Eastern time, so I think that's about all we'll have time for today, unless anybody, the panelists, have anything else they want to say before we go ahead and wrap things up.
I see a couple more, quick questions. I'll just give a quick answer to
okay.
that. One was about the O connector in terms of if we file a patent on them and if they can use it in construction. We did not file a patent, and it can be used, and it's basically a laser cut plate. It's fairly easy to design, and so you're welcome to use that connectors in practice. And the second one was the question was about if you have considered using friction between unbonded tendon and the duct. I don't think this is an option that we even considered, and in terms of reliability, I don't think there's enough information to, I don't know, the question is asking us if we consider this as some kind of a means to address the losses in pre-stressing. But one thing I would say is that in most of the tests, we actually monitor the pre-stressing and we report the data back, and you don't see any influence, or at least any significant influence of the friction coming from the duct to the tendon. So I think that's all. Go ahead, Susie.
I just want to add something to the friction question. I mentioned earlier that there was a Span Creek base connection that we were involved in the development of. There's actually there is a patent on that particular connection, but you can see it in the IPC approval that Spancrete holds on that connection, and you can see that friction connection was actually based off some eccentric braced frame type of research that was done at Berkeley years and years ago. So the concept of a friction connection absolutely works, but you need to make sure it's reliable. In our case, we used a brass plate to get us that reliable friction.
All right.
Okay,
thanks
is there
everybody.
anything else before we wrap it up?
No, thanks for hosting this webinar. It's good.
Oh, thank you to the presenters for the great presentation. Thank you to everyone who attended.
And I would just encourage all the practicing engineers who are listening, go do it. It's really fun and it's really interesting, and it allows you to think hard, but it's very straightforward.
All right, thanks, Lucy.
Thank you, everyone.